Next part is section 11.11, modeling with differential equations. So example 28, we are told that the rate of increase of a population P of microorganisms at a time t in hours is given by the following differential equation. Initially, the population was of size 8. Find a model for P in the form P equals A, e to the power 3t, stating the value of A. So without spelling it out, they are asking you to go from this to that, undo that differentiation, solve that differential equation. So dp dt is equal to 3p. So remember, these act as our y's, dy dx's. So p's are as if they were y's, so we can move the p across. And t's are like x's, so we need to move them across onto that side. We'll leave the 3 on that side. So you've got dp over p is equal to 3 dt. Put the integral symbol. So this is like 1 over p if you prefer to see it like that. So that will go to ln, and that will go to 3t. Let's just do it. A natural log of p. Don't need the modulus symbol, put it there, because population is always going to be positive. And this is 3t plus c at the end. Now clearly it doesn't look like this yet, so what we need to do is move that, replace that c with ln a. So it's, you can call it something else as well, but eventually it might be called as ln a. That's one way of doing it. There you go. Okay, so we are going to move the a across and combine them. So you've got ln p minus ln a is equal to 3t. So it's ln of p over a is equal to 3t. So give it an e. So you've got p over a is equal to e to the power 3t, giving us p is equal to a e to the power 3t. So luckily my a that I chose here is exactly the same as their a, but if it wasn't, then maybe you would have to choose it, rename it as a1 and then relabel it. So this is part A. Find to the nearest 100. Oh right, so we've got initially the population was of size 8, so at time 0 p is equal to 8, so this allows us to find the value of a. So let's sub these in. 8 is equal to a times e to the power of 0, e to the power of 3 times 0 with 0. That will give me 1, so a is equal to 8. So the actual equation is 8 e to the power of 3t. So the value of a is 8. So part B, find to the nearest 100 the size of the population at the time t equals to 2. So you've got to replace that t over here with 2. So it's 8 e to the power of 6. So 8 times e to the power of 6 is 3227.4. Obviously, we'll write it to 3 significant figures, unless they tell you to do something else, which they haven't. So, oh no, to the nearest 100. So it's 3, 2, and that's to the 2 significant figures, which is the same as to the nearest 100. Find the time at which the population will be 1,000 times its starting value. So the starting value is the initial value of 8. So 100 times that, no, 1,000 times. So P is equal to 8,000. So let's substitute 8,000 into the equation that we are working with. So it's 8,000 is equal to 8 e to the power 3t. So e to the power 3t divided by 8 to give you 1,000. 3t is equal to natural log of 1000. So give it ln both sides. T is equal to 1/3 natural log of 1000. So ln 1000 divided by 3. That gives me 3 is equal to 2.3025. Now working in hours, so change it into more accurate. So 2 hours. 2 hours and 18 minutes and 9.31 seconds. So 18 minutes rounded down. State one limitation of this model for large values of t. So this model predicts as the time increases, so as t gets really big, then the population gets really big, and it's just impossible for this species to expand exponentially because of the restrictions of disease, a lack of food, lack of space to continue to grow. So that is not realistic. Okay, let's move on to example. Example 29, you've got a water in a manufacturing plant is held in a large cylindrical tank, and you've got the dimensions of a diameter 20 meters is shown on the diagram. The water flows out, so the volume is reducing and it flows out of the bottom of the tank through a tap at a rate proportional to the cube root of the volume. So what it says, the dv dt, so the rate of change of volume of the liquid in the tank is going to flow out, so it's going to be minus. Let's use some k, but they can notice they're using little k here, so maybe use a different letter, or maybe capital K, proportional to the cube root of volume. So this is the rate of change of the volume, so the amount of liquid inside the tank. Show that t minutes after the tap is open, dH dt is equal to minus k cube root of h for some constant k. So dH dt, we need to write down the chain rule connecting that. So like I said to you also before we do that, when they mentioned something like volume, might as well remind ourselves of the formula for the volume. So it's usually, if it's a cylindrical tank, it's going to be radius that's involved, not usually. Okay, so it's pi r squared times h. So it's pi r squared times h, but r is constant, so it's going to be r squared is 100, so it's 100 pi h. So this is the volume of the water inside the tank. If I differentiate it, because as soon as you mentioned some formulae, why not differentiate it? You've got a variable of h, so that will just go to 100 pi. So that means 4. Okay, so let's set up the chain rule here. So how is volume, and so dH is connected to the other to the volume, so dH and dt and dv, how are they connected? So the other variable that we mentioned here is volume, so it's dv. So it's definitely the chain rule we could use. We are told that dv dt is this minus some constant k and v to the power of a third, and dH dv is 1 over 100 pi, so that's flipped. Multiplied together. So you've got minus k over 100 pi, then v to the power of a third. No, it doesn't look anything like what we want, apart from the fact that we've got a cube root here, and then we've got minus k. The idea is to now replace your v's with the formula involving h. So if v is equal to 100 pi h, if you give it the power of a third, then you will have 100 pi to the power of a third times h to the power of a third. So you will have minus k 1 over 100 pi times 100 pi to the power of a third, which is a cube root, and this is a cube root of h. So if you notice, this looks quite complicated, but what they've done, this here can be replaced with a k. So k, little k, is equal to my big K over, well, times 100 pi to the power of a third over 100 pi. You actually can combine it into 100 pi all to the power of minus 2/3, but that's fine, leave it like that. Okay, so part B, we are asked to show that the general solution to this differential equation may be written as, let me just find a piece of paper, I don't think I've got enough. Oh no, I've got something. That can be written as h equals p minus qt to the power of 2/3, where p and q are constants. There you go. Okay, so we are asked to solve it, and so clearly we've got a nice equation, dh dt equals to some k and then h to the power of a third. I'll write it rather than cube root. So we're going to separate the variables like we learned in the previous section. So dh acts like your dy, h to the power of a third can be moved this way. Dt can be moved onto that side. Okay, and minus k is already there. So on the right hand side you've got minus k dt. On this side you've got h divided by h, I put 1 over h to the power of a third, dh, put the integral symbol. So this can be brought to the top to give me minus 1/3. And this one you can put minus k dt. You can put the minus in front. So add 1 to the power, divide by that power. So it's going to be h to the power of 2/3 over 2/3 is equal to minus kt plus c. So multiply it through, you've got h to the power of 2/3 is equal to minus 2/3 of kt plus 2/3 of c. That can be replaced with another variable. We are asked to make h the subject, so we need to undo the 2/3 power, so we're going to raise it to the power of 3 and square root it. So it's h is equal to, and over here we could put minus 2/3 kt plus 2/3 c to the power of 3 over 2. Yeah, and I think I've misread it, that 2/3 doesn't make sense. Should put my glasses on. Okay, so 3 over 2. Now, what's different here? Well, we've got a bracket with the same power, 3 over 2. And they've got some p, so we'll call that p, and that q, with a minus, obviously. So we can write it as p is equal to our 2/3 of c, that initial constant that we use, and q is equal to 2/3 of k. We'll have h is equal to p minus qt to the power of 3 over 2 as required. Okay, in part C we are told that initially the height of the water is, so it's t is equal to 0, h is equal to 27 meters. And then 10 minutes later, so then t is equal to 10, because we are all measured in minutes, I think. Yeah, must be. And h is equal to 8. Find the values of constant p and q. So we're just ready to substitute these values into the formula. So 27 is equal to P minus Q times 0 to the power of 3 over 2. And over here, 8 is equal to P minus 10Q to the power of 3 over 2. So from this one, we've got P to the power of 3 over 2 is equal to 27. So we're going to cube root it and then square it. So P is equal to 27 to 2/3, which gives me 9. So now we've got to put 9 into that. Again, we can just undo that. So put 2 to the power of 8 to the power of 2/3 gives me P minus 10Q with P equal to 9. This will take you to 4 if you put it in the calculator. 9 minus 10Q. So 10Q is equal to 9 minus 4, which is 5, giving Q a half. So altogether, we've got P is 9 and Q is a half. So H is equal to 9 minus a half T to the power of 3 over 2. Okay, last question on this is part D. Find the time in minutes when the water is at depth of 1 meter. So that's part C. No, part D. So part D, H is equal to 1 meter. I want to find what time it happens. So we need to solve. Remember, this is our equation, 9 minus a half of T to the power of 3 over 2. We can solve this when H is equal to 1. So undo that power, so give it a power of 2/3, which is not affecting 1, still 1. So 9 minus a half T, so a half of T is equal to 9 minus 1. So T is going to be 8 times 2, which is 16 minutes. So I believe this is the last example before exercise 11K. Enjoy.